Okay, so our last topic would be about multivariate convex analysis. So we will first extend our analysis for convex functions, and we will talk about how we deal with multivariate functions, and then lastly, give you some examples about applying the principles. So solving single variate NLP is good, but we need to do something else, okay? We don't want to just focus on a single variate world, but solving single variate NLP still help us a lot, especially in helping us understand the principles. An optimal solution either satisfies the first order condition, or somehow if it is at the boundary, then maybe we have no idea whether it satisfies the first order condition or not. Okay, so that's why for boundary points, we always need some careful consideration or special consideration. Also, we know if the NLP is a convex program, a feasible point satisfying the first order condition would be optimal. So that's something we already know. These above facts actually applies to multivariate nonlinear programs. It's just that we need to have some ways to deal with the fact how a multivariate function may be convex, concave, or neither. So we actually have this definition, okay? Because for definition for convex, concave functions, when we define it, it's already defined for multivariate functions. But still, we want to have some properties about differentiability. So for twice differentiable multivariate functions, we want to somehow also have some ways to check whether a function is convex by looking at second order derivatives. So let's first extend the notion of derivatives first. Because now we have multiple variables, so now we need to talk about partial derivatives. Suppose we have a function which converts n variables into one variable. Then we may take derivatives with respect to each variable. So the ith partial derivative is this one, which is called partial f over partial xi. This partial derivative can be obtained by consider all other variables as constant and just consider that variable as a variable. So for example, the partial derivative for this function would be if you take the partial derivative with respect to x1, we consider x1 as variable. All others are constants, so we remove it, and the derivative is 2x1. As another example, if you take the first order derivative with respect to x3, then here this one gets away, so you have x2. This one gives you 3x3 square. Okay, and this one goes away. So that's how you get your first order derivative with respect to each variable. So similarly, we may define the second order partial derivatives. Okay, so in that case, for each first order derivative, we may differentiate it again with respect to any variable. So if we do x1 twice, we get this one, and then 2x1 becomes 2. If we do x2 twice, and then the second order derivative with respect to x2, and then x2 goes to 0 because x3 is not x2. For the third one, x3, we get to 6x3. Okay? And also, we may do some cross second order derivatives. So if we do that first for x2 and then for x1, first for x1 and then for x2, we get the same result. It's going to be 0. Okay? And so on and so on. So these are all something old in your textbook of calculus. So I hope I don't need to review too much for you. It's just second order derivatives. Okay? So now one property we have that is typically also obtained when you were doing calculus. But now let's do the review. Is that what we have for second order derivatives is a following fact. So the thing is that if we have a twice differentiable function, then if all its second order derivatives are all continuous, then it doesn't really matter whether you do xj and then xi, or whether you do xi and then xj. Probably it would be not so easy to imagine how a second order derivative may be not continuous. Alright? So that's not a big deal. Because for all functions that we will see in the course, and typically for all functions that we may encounter in practice, we have the above property. Okay, so I leave this here just for to make the slides or the lecture rigorous. But actually, that's not a big deal if we are talking about practical problems. So if we have a single variate problem, we know this function is convex if and only if all its second order derivative is non-negative. So now we want to establish some similar way to check convexity for multivariate problems. So our first question is, well, may we say this function is convex if and only if all its second order derivatives with respect to xi twice is non-negative? Is that sufficient? So the answer is no. The example is here. Let's say we have a function, something like this. We want to check whether it is convex at a specific point, 0, 0. So we may do first order derivative, second order derivative. So for a second order derivative, okay, this one is x2. So for both second order derivatives, we may check that, well, it's positive at our point 0, 0. So somehow that seems to suggest that we are having a convex function at least around 0, 0. But the interesting thing is that actually this is not true. If you really do some observation on the graph, you would see that at 0, 0, that function is actually at a saddle point. Okay, so at some direction, it has a downward curvature, while at the other dimension, it has an upward curvature. So I have no way to draw it on this graph. But anyway, you may take a look at this one and this one. So maybe you would also see that, okay, it's not actually convex. So having both second order derivatives non-negative is necessary, but actually not sufficient. This only implies that f is convex along the two axes, but along the other directions, f may still be non-convex. So we need to have a way to test whether f is convex in all directions. Okay, that needs some other notations. Let's do it in the next video.